Let me Okay, so today we'll be focusing on transverse shear and shear center. Now, in the previous session, we went through derivation of Fletcher formula, okay, or what's called Euler-Bernoulli equation, and I discussed like how various equilibrium equations give us different conditions and introduce us to different issues. So one of the issue which we normally encounter is not having the load applied exactly at a point which would avoid twisting. And we had a very detailed discussion how can we apply the load in such a way that the twisting is avoided. So for example, if we have these axes, what are we saying? We are saying that we imagine this is a random cross section and we apply the load. Which axis is best for the load in order to avoid twisting of the cross section? Okay, so in other words, if I apply load over here, imagine I apply load in this direction over here, what will happen? This will make a lever arm and this section can twist. So I can't apply load in this direction. Why? Because I would have twisting, and then this cross section can deform. So which we don't want. We don't want to introduce unnecessary secondary forces. Okay. So we had a discussion that we should apply load always on the principal axis. And principal axis is actually that axis where if you apply the load, that would avoid twisting. Okay, twisting of the cross section. Now, today we will discuss shear center. Shear center is actually a point where you should apply the load in order to avoid the twisting of cross section. Shear center is not an issue in a symmetrical section, like a rectangular section or a square section which I have drawn over here. You will always try to apply the load at this axis, which is the middle axis. Okay, imagine we are applying vertical load. So vertical load must be applied in this axis, which is the principal axis. However, if you have other cross sections, like channel sections, like parallel Z sections. Okay, so in that case, we have to work out the principal axis and then make the load apply on that axis. Okay, so we have to determine the principal axis. Principal axis can't be just determined through visual analysis. You have to work it out. Okay, so that's an important factor. Before going deeper into shear center, I would like to just give you a recap of what transverse shear is, where the transverse shear is coming from. Okay, because without understanding of transverse shear, we won't be able to understand anything about shear center. So, what is a transverse shear? Transverse shear, and how does it come into being? What is the genesis of transverse shear? The answer is hidden. I will answer this question using this simple example. Imagine we have got a beam which is subjected to a series of loads. Okay, so these loads, this beam would have a bending moment diagram. So imagine, let me draw a bending moment diagram for this beam, something like this, a random bending moment diagram. Now, you see that as you move from one support, imagining that our left support is a reference support, so moving from the left support, what happens? My bending moment diagram is increasing. Okay, it can be decreasing, but there is a variation in the bending moment diagram. In this load condition, we will have a sort of a variation. We will always have a variation in this type of loading. There can be a loading where we can't have variation. Okay, and what is that? Imagine we have a beam which is subject to moments. Now, in the case of moments, our bending moment diagram is a straight line. There is no variation. Okay, but under any other load condition, like under UDLs, what will happen? My bending moment diagram is like this. So this is a variation. Yeah. In the case of concentrated load, we have something like this, and although you see that there is a okay, so this is the shear force diagram. In the case of in the case of concentrated, I'm drawing shear force diagram. I'm drawing bending moment diagram. So I've got a load like this. So this is the curve. Okay. So my point is that under different load conditions we have this variation. There is a moment, it can be higher or lower, and that might be increasing or decreasing. That's what my point is. It's only when the beam is subject to moments, equal moments, that we have got a straight moment diagram and we have got no variation. Now, why am I dwelling so much on this variation? You will see that it is this variation which is generating the shear force. That's why I am trying to make you understand that there is a variation. In bending moment diagram, when you draw, normally in generic loading cases, you always have some variation. So, what happens? That in that case, we have, imagine I take a small portion of this bending moment diagram. Okay, a small portion of this length. On one side, it would have a moment diagram which is shown over here at the cross section. At the cross section, we have, so this beam is under compression. This beam is under compression above the neutral axis and it's under tension below the neutral axis. So I can draw the stress profile as this one, isn't it? Okay, this is the top one is showing compression and the bottom one is showing tension. So these are my stresses. Okay, so this can be stress times area. Every cross section is under either compression or tension. What I am saying is that if I have a structure, okay, and I bend it, what will happen? The region below the neutral axis is under tension, and the region above the neutral axis is under compression. So that's where the compression and tension is coming from. Okay, these are the stresses. These stresses we derived previously. Okay, in our previous lecture we derived the flexural stresses, and these flexural stresses, they are varying linearly. Why? Because we have got m, y or I. Y has got a power 1, so they are varying linearly. So this is the stress profile. Okay, this is the stress profile of this region, which is having a length dx and area a dash. I've also shown it over here. This is the region. We take a small region out of the length out of this length. Okay, so we take a small region. This region has got some stress on this face and some stress on this face. So I've taken this out. It has got some stress on this face and some stress on this face. Obviously, this is gonna hang down like this, so it will have tension at the bottom and compression at the top. So we are saying that there is a stress compression which is applied above the neutral axis, and there is a tension stress which is applied below the neutral axis. Now, that's done. Now what we are saying is that is there any difference between these two stresses at these 2 points? Okay, so this is the same at this point and this point. Is there any difference between them? That is what we are trying to find out. Okay, this stress and this stress, are they both equal, or is there any difference between them? The answer is that there is a difference between them. Why? Because what is this stress? This stress is m, y over I. This is dependent on moment, and moment at this point is different from moment at this point. There is a slight variation. Okay, so if there is a slight variation, so obviously they are different. Okay, so the stress over here is different from stress over here. Okay, so there is a variation. So we take summation of all forces in this direction equal to 0. Summation of all the forces in this direction we take equal to 0. Now how do we work that out? We have stress dash, imagine this is stress dash times dA integral. Okay, so this is our stress dash A, and this one is our stress, and the area of cross section is A. It's not necessary that this is a rectangular. This cross section can be of any shape. I've just drawn rectangular for convenience, but it can be of any shape. So stress dash times dA dash minus stress A dash, which is the force over here, minus that difference which is coming from this force and this force. And what is the origin of that difference? The origin, as I said, is the moment. Difference in moment. Moment is varying. So that we call tau, which is a stress, times t dx. In other words, we say that we take a portion of this cross section, that is t, this is dx. Okay, this is, I've drawn it in 3D. So this is t and this is dx. So t times dx is that difference, because the forces have to equate to 0. So tau times t dx, that is the difference, and this must be equal to 0. Now imagining that the moment at this point is bigger, just an assumption, so this is m plus dm, and this point is just m. Why am I calling it differential moment m plus dm? Why? Because these are dx, a small infinitesimal distance dx apart. So m plus dm times y over I into dA prime. That is this is what's called the. So this is actually what we have done is we have put the value of stress dash, and stress dash, for your convenience, I have written it over here. From a previous class we worked it out, m y over I. So this one minus this one will come as it is, tau dx. M and m, they cancel out, and we end up with the m y over I dA prime. and this is minus tau t dx. This one will go on the other side, tau in the end. dm we can bring out of this integral. Why? Because the moment, the area dA bar is not dependent on dm. That is important to appreciate. That's why dm is like a constant in this integral. So we can bring it out. This dx, then dx you can divide both sides by dx. Over here it will get cancelled. T comes over here. So dm by dx is v, which is shear. Okay? We know from our MOSII that dm by dx, the rate of change of moment, is the shear. Okay? So v, what is this? Y times dA bar. This is actually the first moment of area. So in other words, we are saying that we take a small portion and we take a moment of that with respect to this axis, the neutral axis. So that is your Q, which is y dA prime, and divided by IT. So this is our shear equation. So from this explanation, it is concluded that the shear is coming from the change in the moments. The change in the moment is actually giving you shear. So, as I said over here, if you have moments applied on both sides, they don't give you any change, and hence there is no shear in this beam. But if you have a different moment applied over here, this is my moment diagram, and that is also waving. Okay, this is the moment diagram. Sorry, this is. Sorry for this. This is the moment diagram for UDL. This is the moment diagram for a concentrated load on a simply supported beam, and both of them, you see there is some variation always in the moment, and that's why you have got shear force. And if you want to find out shear between any 2 points, you take the difference in the moment, okay, and divide it by the length dx, you will get the shear, and that's what we have learned in our MOSII. So this is the shear equation, which is called VQ by IT. This equation is telling us that the shear at any point in a beam, the shear stress at any point in a beam is equal to shear times Q. Now Q is the cross section, Q is dependent on cross section. Okay, divided by I and T. I is the moment of inertia of that cross section. So, and T is actually the width of the cross section. So, V, I and T, they are constant at a particular point within the beam. Okay, they don't vary. Or in other words, V, I and T, they don't vary along the length. Sorry, my mistake. I and T, I is the moment of inertia. Okay, and T is actually the width. Now, if you have a rectangular cross-section beam which is having a cross-section constant all along the length, then your moment of inertia is constant along the length. T is constant, which is the width, that is constant along the length in case of a rectangular beam having same cross-section along the whole length. Shear depends on the length. You find out the shear. Shear is a function of the length. So shear varies with the length, and Q also varies but Q varies along the cross section. Q will vary along the cross section, it won't vary along the length if your cross section is constant along the whole length. So let me give you an example. Imagine I have got a simply supported beam which is subject to UDL, some W, load per unit length, and it is having a cross section, a simple rectangular cross section which is of width B and height A. Now this beam is of length L. So the shear diagram for this beam looks like this. This is SFD. Okay. I for this one is B inch cubed by 12. T is equal to B. Okay. So in this equation, my I is constant along the whole length. T, which is the width B, that is constant along the whole length. Why? Because I am assuming that the whole length is having a rectangular cross section. B is varying along the length. Okay, and Q is actually it is constant along the length, but Q is varying at a cross section level. Now it is important to understand what Q is. Q if I have got a rectangular beam having width B and depth H, Q is normally AY bar. Now what is this A? This area is actually dependent. This area is actually the portion, dependent on portion corresponding to which you want to work out your shear. In other words, imagine I am trying to find out my shear at this point. As you can see from this equation, that as you move down, the dm, this stress, the stress is changing. The stress value is changing, isn't it? You have got one stress over here, you have got another stress over there. Yeah, and as you come down, the difference between the stresses, that is changing. So similarly, your shear, as you come down is also changing. Although the whole cross section is subjected to one shear force, a resultant shear force, which you determine from your shear force diagram. This shear force diagram, the shear which you get from this shear force diagram, that is a resultant shear of the whole cross section. Okay, that is the resultant shear of the whole cross section. But this equation is telling us that as we make our way downwards, starting from the top fiber of the beam cross section and move towards the neutral axis, our shear is changing, and until we reach to the neutral axis, okay, where our shear is 0. The difference, because please make it in your try to understand that shear is actually this shear is actually the difference between this force and that force. Okay, that shear is the difference of this force and that force. These two, we have taken a small portion dx from this beam. A small portion dx is taken. This dx is this is that dx. Okay, and on one side we have got one magnitude of stress. On the other side we have got another magnitude of stress. The shear, we said, is equal to the difference between these two forces. But as we move down, this difference changes. You can see that over here the difference can be maximum. Then as you move down, the difference reduces. Why? Because you have got these forces getting reduced until you reach here where the difference is 0. Because this is 0 and this is 0. 0 minus 0 is 0. And then you move further down, and then again difference starts increasing. Okay? And it reaches maximum when it comes over here. So, in other words, the shear distribution on this one is parabolic. The shear distribution on this one is parabolic. And what you get from your shear force diagram, that is actually the resultant, or in other words, the maximum shear. Okay? So, that's what I am saying, that we have two things. One is the horizontal. This, you can see, this is a horizontal shear. Okay? So if we assume that this beam, we have got this beam, imagine, and it has got a small portion which we have taken over here. Okay? In this beam, if we assume that this beam is made up of small elements, rectangular elements, which looks imagine our beam is made up of elements. Okay, we take a small element over here. Okay, so let me show you. Let me zoom in. Imagine I've taken this element, and this is over here. This element at this point will have a certain horizontal shear, which is, imagine in this direction. This horizontal shear, based on equilibrium, must have an equal force in this direction, which is so that for them to cancel out. And you can see this makes a couple. So in order to counteract that, we must have a force, a couple in the opposite direction. So we have this is the horizontal shear. Okay, and on the cross section, based on equilibrium, we have a vertical shear. When you, in your MOSII, you would cut a section, and on the section you would say that there is a moment and shear. Okay, this shear is actually this shear which is coming out from the equilibrium of this element. Okay, so this horizontal, these are horizontal shears, and correspondingly we have vertical shear on the cross section. Okay, I said that this vertical shear is different at different location of cross sections. This is different. The point, okay, so if you are taking this portion only, so this will have different shear, and as you move down, this will have, like, the shear will keep on changing. I told you that this is parabolic, it changes parabolically. The shear which you get from the shear force diagram, that is actually the resultant shear. Okay, so this Q, the Q is actually telling us which point on the cross section we are interested in, which point within the cross section are we interested in working out our shear. Because as I told you, the shears are different in different locations. Okay, so it is important that you understand the mechanics of this formula. I'll repeat once again what this formula is telling us. It has got a resultant shear V. This is the resultant shear V, which you get from the shear force diagram, and it is resultant of the whole cross section. Then it has got moment of inertia of that cross section, it has got the width of that cross section, and it has got the Q, the first moment of area of that cross section. Now if I am interested in finding out shear at this location, okay, if I am interested in finding out shear at this location, what should I do? I should adjust my Q in such a way that I get my shear at this location. And how would I do that? I would find out my Q as area. So imagine this is h by 3. This is at a distance h by 3 from here. Okay, so I will take the area A, which is this times h minus h by 3, which is 2 by 3 here. This is this is h by 2. Okay, imagine this is 1/3 of h by 2. So 1/3 is h by 6. This will be h by 2 minus h by 6. How much is that? 1 by 2 minus 1 by 6, which is h by 3. So the area of this box is h by 3 . That is the area times y bar. Y bar is the centroid of this box, and that centroid is how much? H by 2 minus h by 6, isn't it? This centroid of this box from the neutral axis.
So shaded portion is centroid.
Yes, because I'm interested in finding out my shear at this point. So I take my Q corresponding to this one. Okay, so this is h by 2 minus h by 3 by 2, which is h by 2 minus h by 6, and that will give me Q. And from there I can just plug now all the values in my top, and I will find out my shear stress. Now the question comes, do you have any question? The question comes, why are we interested in shear? What's the use of finding out shear at different locations? Why bother so much about finding out shear at different locations in the cross section? The answer to this question is, let me give you an example.
पूरे एलिमेंट को रिप्रेजेंट करेगा।
Sorry?
जो क्रॉस सेक्शन होता है ये पूरे एलिमेंट को रिप्रेजेंट करेगा।
This cross section?
यानी कोई भी क्रॉस सेक्शन कर लेते हैं हम एलिमेंट के किसी भी पार्ट से, तो क्या वो पूरे एलिमेंट को रिप्रेजेंट करेगा कि बस उसी एक पोर्शन को ही रिप्रेजेंट कर रहा है?
In the case of shear, this equation phi is equal to VQ by IT. Okay, this is it depends where you want to find out your shear. Okay, whether you want to find out the maximum shear stress within the cross section. So then you can take Q is you can take simply Q as the maximum. You are interested, imagine, in finding out maximum shear within the cross section, maximum shear. Okay, so that would be equal to, and this is h by 2, so your Q then would be equal to B times h into h by 2 by 2, which is h by 4. Now this is with respect to the whole cross section. Why? Because you have taken Q with respect to the whole cross section. So this is the maximum shear within the cross section. The previous one I was doing, that is with respect to a small portion of the cross section. But the question is, when do we need this small portion? That example I will give you now. Imagine I have two planks. Okay, one is like this and one is like this, and I have glued them together at this point. These are two pieces of wood. I have taken them, one I place over there and one I place like this. I glued them like this. Okay, yes. Now this is one piece of wood, this is another piece of wood. I have put glue over there and I have joined it. Okay, now the problem is, I want to find out whether the glue which I have applied over here is strong enough to take the load. And what is that load which the glue will take at this point? At this juncture, what is that load which the glue will take? Horizontal shear. So it's the horizontal shear I am interested in. It can be like, imagine I have nailed it over here. I have put series of nails over there. Now I want to find out how many nails should I put in order to take the horizontal shear. So that's why when I join different components together, I produce weak zones. And those weak zones, they are actually points which can fail. Those are the regions which can fail under shear, and I have to check them, okay, whether they fail or not. You understand my point? So that's why we are interested in shear, in finding out our shear at this point. The glue shear strength we will get from the manufacturer, okay, because they do a lot of tests on the shear and they will tell us that this can take that much shear. But the shear which we are getting from the actual applied load, that we have to make sure that that is less than the shear strength of the glue. Clear? So that is actually the final thing in this is if we bring this star, this T over here, what we get is, imagine this, and this is equal to BQ over I. This is called shear flow. I've just multiplied, this is stress. I multiply it with the width, okay, the width of the section, and I get shear flow. So this is called my shear flow. This is, its unit is load per unit length, because this is load per unit area, isn't it? You multiply T with it, so you get load per unit length. Okay, so that is, so this is the end of this topic, and we have to do now an example.